Good evening, class. Tonight, I would like to talk about Stereochemistry at Tetrahedral Centers. This topic can be found at Chapter 6 of your textbook, Organic Chemistry by John McMurray. Here is the outline of discussion for this chapter. First, an overview of the classification of isomers, followed by a definition of what constitutional, conformational, configurational, and stereoisomerism is. And finally, we shall be delving deeper on chirality and handedness by tackling the important subtopics such as optical activity, can involve pre-log sequence rules, enantiomers, diastereomers, and Meso Compounds. The following diagram shows the classification of all isomers that can be found in organic chemistry. We have constitutional isomers. Constitutional isomers are compounds having the same chemical formula but different branching structures. Examples of constitutional isomers are this compound, pentane, 1, 2, and this compound. So these two are constitutional isomers. They have the same formula but different branching structures. Configurational isomers, on the other hand, are organic compounds having the same chemical formula, similar chemical structures, but different orientation. Other configurational isomers, we have stereoisomers, conformational isomers, and geometric isomers. Geometric isomers, starting from geometric isomers, these are organic compounds that exhibit either easy isomerism or cis-trans isomerism. Geometric isomers are often found in alkenes. Conformational isomers, on the other hand, are also called rotamers. Examples of rotamers are the eclipsed, gauche, and staggered conformation in ethene. So basically, conformational isomers only differ on the rotational aspect of its structure. In this chapter, we shall be talking about stereoisomers. Under stereoisomerism, we have chirality at tetrahedral centers, axial chirality, and Meso Compounds. Of these three, we shall only be talking about chirality at tetrahedral centers and Meso Compounds. Axial chirality is a topic that belongs to the subject on advanced organic chemistry, which is not covered by this course. Under chirality at tetrahedral centers, we shall be talking about what enantiomers are and what diastereomers are. Also, we shall be relating diastereomers to epimers, which would be discussed in your biochemistry class. Before delving more to our discussion, I would like to introduce a certain compound to you. So, this compound, these two compounds, as you can see, they have the same chemical structure but different orientation at this carbon. So in this particular compound, hydrogen is situated at the front and methyl is situated at the back. On the other compound, methyl substituent is situated in the front, whereas hydrogen is situated at the back. These two compounds are called R-methamphetamine and S-methamphetamine. As you can see, they have the same name, but the only difference is just the orientation of its substituents. In the real life scenario, there is a huge difference on its chemical and physical properties because R-methamphetamine is used as an inhaler in Vicks VapoRub, whereas S-methamphetamine is the illegal drug which is most commonly known as shabu. So as you can see, even with a slight difference in the orientation of its substituent, there is a huge difference on the impact of stereoisomers. Its physical and chemical properties are greatly affected. Another example is the following molecule called thalidomide. So these compounds are designated as S minus thalidomide and the other one is R plus thalidomide. Thalidomide has been a very controversial compound because it has been marketed by a pharmaceutical company in Europe in the 1970s, which led to a very great disaster. Thalidomide, or particularly the R plus thalidomide, has been marketed as a medication for morning sickness of pregnant women. So this is the structure of R plus thalidomide, wherein the nitrogen is situated at the back and the hydrogen is situated in the front, whereas in the S minus thalidomide, nitrogen is situated at the front and hydrogen is at the back. R plus thalidomide in pharmaceutical terms is designated or is named as Epimers. Epimers are the pharmacologically active forms of a drug. On the other hand, in pharmacological terms, Distormer is the other form of a substance, or distormer is the other form of a medication which is either inactive or possesses side effects. So the controversy during those times was that thalidomide has been marketed as a racemic mixture. When we say racemic mixture, there is a 50-50 ratio of your Eptimer and distormer. And during those times, little did they know that S minus thalidomide was actually a teratogen. Teratogen is a compound that causes deformities in fetuses. Due to the introduction of thalidomide in the market, several fetuses in Europe has been deformed due to the use of thalidomide. And it was one of the major controversies in the pharmaceutical industry in the late 1980s. As you have all observed, when writing stereoisomers, we have to designate its orientation. So, when writing or drawing stereoisomers, we have to make use of either the bold arrow, this one, or this one, to indicate that the substituent is situated at the front. On the other hand, this designation indicates that the substituent is situated at the back of the molecule. One of the most notable characteristics of stereoisomers is that they possess chirality. Chirality refers to the optical activity of a molecule in its interaction with light, and it always happens when there are 4 different substituents in a tetrahedral carbon. Compounds possessing chirality are enantiomers and diastereomers. Enantiomers, by definition, are mirror images that are non-superimposable. Suppose we have these following compounds. In the first example, carbon has 4 substituents connected to it, fluorine at the top, chlorine here, bromine by the front, and iodine at the back. The other substituent, on the other hand, has fluorine at the top, chlorine at this position, iodine at the back, and bromine at this position. Basically, these 2 compounds are mirror images of each other. Suppose this broken line at the center of the page is our mirror. The mirror image of compound 1 is compound 2. The ball and stick model representation of the compound is shown in the following. For compound 1, we have this ball and stick model. This atom corresponds to fluorine. This one corresponds to chlorine. The red one corresponds to bromine, and the purple one corresponds to iodine. Its other representation is this one. We have chlorine here, fluorine, iodine at the back, and bromine at the front. Take note that these 2 compounds are mirror images of each other. Now, what does non-superimposability mean? Non-superimposability means that you cannot stack them on top of each other in such a way that they assume the same shape or conformation. A very fine example of enantiomers are our left and right hands. The mirror image of our left hand is our right hand, but take note that both of our hands are non-superimposable on each other. Meaning, if you place your left hand on top of your right hand, you will not perfectly stack both your left and right hands because they are not essentially the same. So that is basically same with enantiomers. Even though enantiomers are mirror images of each other, they are not essentially the same and they are not superimposable on top of each other. So in the next example, or in the compound 2, this compound 2 is rotated in such a way, rotated 180 degrees in order to match the orientation at compound 1. So these 2 and these 2 are basically similar orientation. But take note that in this orientation, we have fluorine at the top, chlorine at this position, but iodine is now at the front and bromine is at the back. Mirror images are not essentially the same, and that's why they are called non-superimposable. So for this compound, this carbon is the chiral center, and for this compound, This carbon is its chiral center. Now, diastereomers in the context of organic chemistry are non-mirror images and non-superimposable organic compounds. Diastereomers are often observable when there are two or more chiral centers. Let's take these two molecules here. Molecules 1 and 2 are enantiomers because they are mirror images of each other. Enantiomers 3 and 4, or compounds 3 and 4, are also enantiomers because they are mirror image of each other. So when chlorine is situated at the front here and bromine is situated at the front also, its mirror image would be the opposite. So chlorine is situated at the back and bromine is also situated at the back. So that is its mirror image. On the other hand, in compound 3, chlorine is situated at the front and bromine is situated at the back, and its mirror image would be the opposite. Chlorine is now at the back and bromine is at the front. So basically, compounds 1 and 2 are enantiomers and compounds 3 and 4 are also enantiomers. But how about compounds 1 and 3 or compounds 2 and 4? They are not enantiomers. They are called diastereomers because they are not mirror images and they are not superimposable. The most relevant analogy for this one is when we think of enantiomers as our left and right hands, diastereomers are basically the left and right hands of your friend. Your left and right hands are not essentially the same with the left and right hands of your friend. They are not mirror images and they are also not superimposable with the left and right hand of your friends. So basically, they all have the same structure and branching of substituents, but the orientation are very different. Now, how could we know how many are the diastereomers in a particular compound? Take note that the total number of diastereomers that can exist in a given compound is equal to the number of its chiral centers. This set of enantiomers under A is one set of diastereomers, and this set of enantiomers at B is also another set of diastereomers. So for this type of compound having two chiral centers, there is an equal number of diastereomers corresponding to the number of chiral centers that are present in a molecule. So if you have two chiral centers, essentially it means that you have two diastereomers. If you have three chiral centers, that means that you also have three diastereomers. Now, in relation to diastereomers, I would like to talk about epimers. Epimers, which you will be learning in biochemistry, are basically carbohydrates that vary in one position for the placement of the hydroxyl group. Suppose we have these two examples. We have D-glucose and D-galactose. Glucose and galactose have 1, 2, 3, 4 chiral centers. Epimers are basically forms of carbohydrates that only vary in one position. So in the context of D-glucose and D-galactose, D-galactose is an epimer of glucose at carbon number 4 due to the fact that it only differs the orientation of its substituent at carbon number 4. At carbon number 1, you don't have a chiral center at this position. At carbon number 2, you have a chiral center, but it's similar orientation with that of D-glucose. In carbon number 3, you also have the same orientation for this chiral center, but in carbon number 4, the orientation is different. So basically, these two are epimers of each other, or D-galactose is an epimer of C4 epimer of glucose, and epimers are just a subset of diastereomers. Let's have a brief exercise in identifying chiral centers. So basically, chiral centers are found in tetrahedral carbon, and when we say tetrahedral carbon, the hybridization is sp3. Furthermore, chiral centers are carbons having 4 different substituents bonded to the carbon atom. So let's identify chiral centers in the given set of molecules. So in number 1 example, the chiral centers are this carbon, and this carbon. So we have carbons 2, 3, and 4. In the second example, there is no chiral center in this molecule due to the fact that the hybridization of these carbons in aniline is sp2 and not sp3. In the third example, there are no chiral centers in this example due to the fact that you don't have four different substituents bonded to each carbon atom. So let's examine carbons 1, 2, and 3. So in carbons 1, 2, and 3, you have two hydrogens. Basically, when you have two recurring substituents that are bonded, or two recurring atoms that are bonded to a central carbon, it is automatically not a chiral center. Examining carbon 3, similar scenario. Examining carbon 2, carbons 1 and 3 are essentially similar substituents. So basically, carbon 2 is not a chiral center. In the case of example 4, there are four chiral centers here. This chiral center, this, so we have carbons 2, 3, 4, and 5 as your chiral center due to the fact that they have different substituents bonded to each carbon. So here you have three chiral centers. In this you have 0, 0, and 4 chiral centers. Now, one of the most important aspects in learning stereoisomerism or stereochemistry is the assignment of chirality. There are two ways in assigning chirality. One is by using absolute configuration, and the other one is by using relative configuration. When we talk about absolute configuration, we are referring about the notations plus, minus, and L and D. L and D essentially means dextro-rotatory or levo-rotatory. Absolute configuration is based on the rotation of plane polarized light upon its interaction with chiral compounds. On the other hand, relative configuration refers to the R and S assignment of chiral compounds. And relative configuration is only based on the Ken-Ingold-Prelog sequence rules, which takes into account the priority of substituents that are bonded to your chiral carbon. First, let's talk about absolute configuration. As given by the definition, it refers to the rotation of plane polarized light upon interaction with chiral compounds. In this definition, we have to take note of two terms. The first term is rotation and the second term is plane polarized light. So basically, what is a plane polarized light? Take note that light is composed of both an electric field and a magnetic field. Light as a wave is represented by this given figure having both electric field and magnetic field. In order to determine the absolute configuration, we have to use an instrument called polarimeter. A polarimeter has what we call a polaroid filter that only allows one component of light to pass through. For example, a vertical polaroid filter will only allow the electric field component of light to pass through and blocking the magnetic field component of light. So when this light wave passes through the polaroid filter, it is being polarized and only one component is being allowed to pass through the polaroid filter. The resulting light is what we call a plane polarized light. And this plane polarized light, this one, is being bombarded to a cuvette containing a chiral compound. So this one is called a cuvette, which holds a solution of your chiral compound. Upon bombardment of your chiral compound by the plane polarized light, the plane polarized light will interact with your chiral compound and would be rotated by your chiral compounds. So initially, your plane polarized light is vertically oriented, therefore it has a 0-degree angle. So this one is your plane polarized light having a 0-degree angle. Upon bombardment with your chiral compound, it is being rotated to a certain degree. So initially, it was oriented vertically like this, but upon bombardment, it is being rotated in this direction. So towards the right or clockwise direction. Upon rotation, it generates a positive, for example, it generates a positive 10 angle in reference to its initial position. So take note that a positive 10-degree angle means that the plane polarized light is rotated to the right. In absolute configuration, when your plane polarized light is rotated to the right, it is designated the notation plus or D. D means dextro-rotatory, which also implies that the rotation of your plane polarized light is to the right. On the other hand, if your plane polarized light is rotated to the left, or when it registers a negative angle like this, negative 45-degree angle, or rotated to the left, it means that the absolute configuration is L or minus, meaning your chiral compound is levo rotatory or rotates plane polarized light towards the left or counterclockwise direction. Absolute configuration can only be known by using a polarimeter. On the other hand, relative configuration makes use of the Cann-Ingold-Prelog sequence rules. Cann-Ingold-Prelog sequence rules, or CIP rules, is a set of guidelines that have been developed to classify organic compounds based on the substituents that are bonded to your chiral carbon. The first rule of CIP sequence rule is substituents with higher atomic number take higher priority. Let's look at this particular organic compound here. In this compound, you have fluorine, chlorine, iodine, and bromine that are bonded to it. So basically, your carbon is a chiral center. Now, based on CIP rules, we assign number 1 to that of the highest priority and number 4 to the substituent having the lowest priority. So in this context, iodine is number 1, bromine is number 2, chlorine is number 3, and finally fluorine is number 4. And by using the CIP rules, we have to reorient the molecule in such a way that your lowest priority is at the back, in such a way that it resembles a steering wheel of a car. So imagine that this organic compound is a steering wheel. This one is your steering wheel, and the thing that holds the steering wheel is located at the back, which is the lowest priority substituent. So in this context, we have iodine situated here, bromine situated here, and chlorine situated here. So based on these orientations, we could see that the direction of the order of the substituents from the highest to the lowest is to the left or counterclockwise. If the substituents' priority numbers are oriented in a counterclockwise manner, the chiral center is designated as S. S for counterclockwise or to the left. On the other hand, if the priority numbers of your substituents are oriented in a way that it follows a clockwise manner, or the direction is to the right, that is designated as R, clockwise or to the right. It's very easy to remember R for right. In order to properly visualize a chiral compound and see the orientation of its substituents, we have to make use of our 3D brains. It takes practice, but in some instances, it would be better to make use of molecular models. For that particular compound, we have fluorine, which is bonded at the top portion, chlorine, which is bonded at this location, this one, iodine, which is bonded by the front, and bromine, which is bonded at the back. Take note that fluorine is the least priority. Therefore, you must reorient the molecule in such a way that fluorine would face, the orientation of fluorine would be facing away from you. So what we need to do is to reorient the molecule like this. As you can see, fluorine is at the back part of the molecule, such a way that you cannot see it anymore. So based on this orientation, we have iodine, bromine, and chlorine. This orientation is situated in a counterclockwise manner. Therefore, the chiral center carbon is designated as S. On the other hand, we have the same compound but different orientation. So we have fluorine at the top position, chlorine at this position, bromine at the front, and iodine at the back. So the previous example was iodine was at the front and bromine was at the back. So in this example, still we have to reorient it in such a way that the least priority would be facing away from you. So reorient it like this so that you won't see fluorine anymore. And as you can see, iodine has the highest priority. So it is number 1, followed by bromine number 2, and chlorine is number 3. And the orientation of these substituents are situated in a way that it follows a clockwise manner, and therefore the chiral center is designated as R, or this enantiomer is an R enantiomer. The second rule for Can-Ingold Krylov sequence rule is that if a difference cannot be found at the directly connected atoms, examine at the next bonded atoms, and so on until a difference is found. Looking at the given compound, we only have one chiral center, which is this carbon. So this carbon has a methyl substituent situated at the front and hydrogen situated at the back. Basically, hydrogen is the least priority, so it's assigned number 4. What we have to determine first, which one is the 1, 2, and 3, or the first, second, and third priority. So bonded to this chiral carbon are also carbons. So looking at the directly connected atoms, you cannot see a difference because they are all carbons. So what we need to do next is to examine the next bonded atoms. So in this context, for the methyl substituent, after carbon, you only have hydrogen which is bonded to it. And in this context, after carbon, you have carbon bonded to it. And at this substituent or at this location, after carbon, you have bromine bonded to it. So basically, this one is your number 1 or the first priority. This one is your number 2, the second priority, and this one is your number 3 or the third priority. In this example, hydrogen is already at the back. So you could assign chirality or assign the relative configuration right away. So the relative configuration of this compound is you have 1, 2, and 3. So it is S because it follows a counterclockwise manner. Another example given here is example number 2. Same with the previous example, you have this carbon as your chiral center, and bonded to it are also carbon atoms. So this one is a carbon atom, this one is a carbon atom, and the methyl substituent bonded at the front is also a carbon atom. But at the second carbon bonded to it, the methyl substituent has hydrogen bonded to it, basically the rank 3. Hydrogen is always rank 4, and in this context you have carbon bonded to it and also carbon bonded to this carbon. You have carbon bonded to it. And finally, looking at the third atom bonded to it, you only have hydrogen here. So basically, this one is rank 2, and you have carbon here instead of hydrogen. So you have this as your rank 1. Basically, this is your rank 1, rank 2, and rank 3. And it is situated in such a way that you have this one, 1, 2, and 3. Still, this compound is also an S enantiomer. So how do we name this type of compound? Compound number 2 is an alkane. So it is an alkane having 1, 2, 3, 4, 5, 6, 7 carbon chain with a methyl substituent at carbon number 3. You can just name it first by writing the chirality or the relative configuration, which is S, and the name of your alkane, which is 3-methyl heptane. So the name of this compound is S3-methyl heptane. How about the absolute configuration? Can we know the absolute configuration just by looking at the substituents bonded to your chiral center? The answer is no. We can only know the absolute configuration when we use the polarimeter in order to determine if it's either dextro-rotatory or levo-rotatory in its interaction with a plane polarized light. Okay, so the third rule by the Can-Ingold-Krylov sequence rule is that triple bonds take higher priority, followed by phenyl group, double bonds, and single bonds. So if you have read your book, the third rule of Can-Ingold-Krylov sequence rule is stated differently, but in essence, this one is the meaning of that rule in your textbook. So basically, triple bonds take the highest priority, followed by phenyl groups, double bonds, and single bonds. Looking at this particular carbon atom, we have a chiral center here because you have 4 different substituents bonded to it. Now, we have to assign chirality to it by labeling these substituents based on their priority. Based on the third rule of CIP, this alkyne takes the highest priority, followed by phenyl group, followed by this alkene, and finally you have this alkane which has the lowest priority. So this compound is bonded in such a way that it follows this type of orientation. So you have 1, 2, and 3. The substituents are arranged in a manner that follows a counterclockwise direction. So basically, the chiral center for this compound is designated as S, or this one is an S enantiomer. Now, I would like to give more examples of compounds having different chiral centers. And I would be assigning the chirality for each chiral center. For compound number 1, we have this chiral center and this chiral center at carbons 2 and 3. So take note that bromine takes the highest priority here, followed by this carbon, and finally this methyl substituent. This position of this carbon is basically like this: 1, 2, and 3. Basically, this one is R. This one is R. How about in carbon number 3? So you have chlorine here, which has the highest priority, and this carbon followed by this carbon atom. Now, if you may ask, why is the carbon situated at the left designated higher priority than the carbon situated at the right? The answer is, if we look at them, they are both carbon atoms. So we have to look further to find a difference. For the carbon situated at the right, what is bonded to it is another carbon atom. However, in the carbon bonded at the left, what is situated to it is a bromine atom. So a bromine takes higher priority than carbon, and therefore this carbon is being designated as number 2, whereas this carbon right here is designated as number 3. So this carbon number 3 has this orientation, which is 1, 2, and 3. It is still R. So both of the chiral centers have an R designation for its relative configuration. So you may ask, how do we name this type of compound? Okay, so basically this one is an alkane or alkyl halide, but you must name it as an alkane. So it has 1, 2, 3, 4, 5, which is 5 carbon atoms. That means the parent name is pentane. And substituents are located at carbons 2 and 3. So 2 bromo, 2 chloro, pentane, and finally we have to indicate the chirality at the start of its name. So at carbon number 2 we have 2R, and at carbon number 3 we also have 3R. Therefore the name of this compound is 2R, 3R, 2-bromo, 2-chloropentane. Let's look at the next example, which is example number 2. In the given compound here, their chirality is situated at this carbon atom because it has 4 different substituents. Okay, where is the 4th substituent? It is the invisible hydrogen, which is located at the front. Okay, take note that we have to assign chirality to it by determining the priority of each substituent. Hydroxyl group takes the highest priority because oxygen takes higher priority than carbon. And bonded to this carbon are carbon double bond carbon and carbon triple bond carbon. Remember in the rule 3 of CIP rules that alkynes take higher priority than alkenes. Therefore, this carbon is designated as 2 and this carbon is designated as 3. And as always, your hydrogen is the least priority, so designate it as 4. So basically, what we have here is this type of arrangement. 3, 2, 4, then at your back is the 1. How should we assign the chirality of this compound when our highest priority is at the back? The answer is we only have to rotate it in such a way that substituent number 4 is located at the back. So rotate this one like this, and carbon number 1 would be, substituent number 1 would be here, substituent number 3 would be here, and substituent number 2 would be here. And finally, your 4th substituent is at the back. So I just rotate it at this direction to get to this type of orientation. So when you get to this orientation, you can assign the relative configuration of your compound. So in this context, we have 1, 2, and 3 situated or oriented in a counterclockwise manner. So basically, this chiral center is designated as S. In example number 3, our chiral center is this carbon number 3, and our first priority is obviously nitrogen, followed by this substituents, and finally this substituents. So this one is situated in this manner, 1, 2, and 3. So this one is also S. In example number 4, we have 2 bromine atoms as our substituents, and the chiral centers are at this carbon atom. So let's assign chirality to it. The first priority would be this one, second priority would be this one, and third priority would be this one. So this carbon is situated in such a way that 4, 3, 2, and 1 is at the back. So all you need to do is to rotate it like this, 2, 3, 1, and 4. Rotate like that. And finally, we get this type of orientation, which is counterclockwise, meaning this carbon is an S. On the other hand, this carbon has these substituents, so the assignment would be this one. This one. Bromine atom is our number 1, this carbon is our number 2, and this carbon is our number 3. Of course, hydrogen is at the back, so you don't need to mind the hydrogen. So this one is very easy. So this one is also S. So what is the name of this compound? It is 1, 2, 3, 4, 5, 6, 7, 2S, 6S, 26 dibromoheptane. The last part of our lesson is about meso compounds. So meso compounds are basically achiral. When we say achiral, meaning not chiral. Achiral compounds having chiral centers. So it might seem ironic or paradoxical to you. It's not chiral, but it has chiral centers. So why is that so? It's because it has a plane of symmetry and that their mirror images are superimposable with each other. When we say superimposable, take note that enantiomers have mirror images that are not superimposable with each other. The RNS enantiomers are essentially not the same, but for meso compounds, its enantiomers are basically the same. And as a result, it is not a chiral compound. It's not a chiral compound. So how could we determine if a certain molecule is a meso compound? So we have 3 different criteria. The first one is that it has 2n chiral centers, wherein n is a positive integer. So what we need to do here is to just find the value of n. The n should be a positive integer and a whole number. Secondly, we also have your compound is atomically symmetrical, meaning it has an internal plane of symmetry. And finally, it has opposite RNS configurations of chiral center. So if these 3 criteria are being met, your compound is a meso compound. Okay, let's have these examples of meso compounds. Meso compounds are superimposable mirror images. Take a look at compound number 1 and compound number 2. Compound number 1 has bromine atoms situated at the front of your molecule, and its mirror image is that the bromine atoms or bromine substituents are situated at the back of the molecule. Now, what happens when you rotate compound number 1 by 180 degrees in its plane of symmetry? So the plane of symmetry of compound number 1 is this line here. And if you rotate it at its plane of symmetry, you will get to this form. And basically, the rotation of compound number 1 results to its mirror image, which is compound number 2. So essentially, you can superimpose compound number 1 with compound number 2. So that is what is meant by superimposable mirror images. Compounds 1 and 2 are essentially the same. It has the same structures and they are superimposable. Meso compounds are not chiral despite having chiral centers. The last part of our discussion would be an exercise on determining if these organic molecules are meso compounds. So let's have example number 1. Does it have a plane of symmetry? Of course, first the first criteria is it has 2n chiral centers. So the chiral centers are this and this. First criteria, 2n chiral centers. So how many chiral centers do we have? We have 2 chiral centers. And we need to calculate the value of n, which is 1. So in this context, n is a whole number. Second criterion is that the substituents are atomically symmetrical. So there's an internal plane of symmetry. So where is our internal plane of symmetry? It is situated here. So take note, if you rotate this compound at its plane of symmetry, you might get similar compounds. Okay, so yes, it has a plane of symmetry. The third criterion is it has opposite designation for its relative configuration, meaning it has R, S, or SR designation and not RR or SS. So let's examine the designation for its chiral centers. For this carbon, you have 1, 2, 3. So this one is R. And for this carbon, you have 1, 2, and 3. You also have R. So this one is RR. So since you have different designation for its relative configuration, the compound or this compound is not a meso compound. Not a meso compound. Let's look at its counterpart. In this context, you have 2n is equal to 2, n is equal to 1. Secondly, it has a plane of symmetry, which is situated here. And finally, does it have alternate RS assignment or relative configuration? Let's examine. So the first one is 1, 2, and 3. This compound is R. The second one is 1, 2, and 3. But this one is at the back, so you have to rotate it. So basically, this one is S. So yes, RS. So this compound is a meso compound. This one is a meso compound and this one is not a meso compound. Okay, how about compound example number 2? So the chiral centers for this molecule are this one. By the way, it might be intriguing for you, but this type of representation or structure is very common in biochemistry. So what is this structure, or what does this really mean is that the structure is like this. So how come these structures and these structures are the same? So take note that if you look at structure B from the top, you would just see this representation. Just look at it from the top portion of the molecule and you will see the representation that is given by structure A. So let's examine if it's a meso compound or not. So first is 2n equals to 2. So because it has 2 chiral centers, so 2. N is equal to 1. Okay, so the first criterion is being met. Does it have a plane of symmetry? Yes, it has a plane of symmetry which is this one here. Yes, symmetrical. The third one is, does it have alternating relative configuration? Okay, let's examine. So for our first example, you have 1, 2, and 3. So this one is R for this carbon. And for this carbon, on the other hand, you have 1, 1, 2, and 3. You also have R. So you have R here. Basically, this one is not a meso compound. Finally, our last example for this chapter would be example number 3. Take note, we have 3 chiral centers here. And we are to examine if it's a meso compound or not. The first criterion would be determining the value of n. So 2n is equal to 3 and n is equal to 3 over 2 or 1.5. So basically this one is not a whole number. So automatically this one is not a meso compound. As a summary of our lesson, we have learned about stereoisomerism. We have learned about the types of isomers, which are constitutional and configurational isomers. And under configurational isomers, we have delve deeper on stereoisomers, which only differ on their spatial orientation for the substituents. And under stereoisomers, we have enantiomers and diastereomers, and also Meso Compounds. Both enantiomers and diastereomers are optically active, meaning they have what we call chirality. On the other hand, Meso Compounds have chiral centers but are not optically active. What is meant by optically active is that it interacts with plane polarized light. Interaction with plane polarized light, which is related to absolute configuration. And there are two types of designation for absolute configuration. You have plus, minus, or L and D. Plus refers to the rotation of plane polarized light towards the right, and minus refers to the rotation of plane polarized light towards the left. Also, D or dextrorotatory refers to the rotation of plane polarized light towards the right, and L refers to the rotation of plane polarized light towards the left. So it's easy to remember. L for left, L for minus. L left minus. On the other hand, relative configuration is the RNS assignment of your chiral centers based on the Cann-Ingold-Prelog sequence rules. Cann-Ingold-Prelog sequence rule, the rule number 1 is substituents are arranged in such a way that substituents having higher atomic number have more priority than those with lower atomic numbers. Secondly, if there are no point of difference that are being seen at the first directly bonded substituents, look at the next bonded substituents until a difference is found. Finally, triple bonds have the highest priority, followed by phenyl group, double bonds, and finally, singly bonded substituents.